once again. So we are now on the second application of first order differential equation, and that is the Newton's law of cooling. So actually we will not only be covering the Newton's law of cooling, but rather the law pertaining to warming as well. So at the end of this presentation, so we should be able to apply the solution of the first order differential equations in Newton's law of cooling applications. The Newton's law of cooling, so it states that the rate of change on the temperature of the body, so with respect to time, so corresponds to the difference between the temperature of the body and the temperature of its environment. So mathematically speaking, so the differential equation that would be formed, so out of the Newton's law of cooling, so that would be the derivative of the temperature, or that is dt, so with respect to time, so over dt is equals to the difference of the temperature of the body, so that is T, and the temperature of its environment, which is the Tm. And of course, so we have the proportionality constant K, so which is a ratio on the rate of the change on the temperature with respect to time over that of the difference between the temperature of the body and its given environment. So that is a property of a certain material, so which does not change. So whatever would be the scenario, or whatever would be the environment that we are going to subject a certain body or a certain object. So looking at the differential equation, so for pertaining to the Newton's law of cooling, so we can see here that the temperature of the body, okay, could there are only two things that could possibly happen. So it could either decrease its temperature, or it cools down, or there would be an increase on the temperature, so where it warms up. But based from those things, we have to take note that the limit on the change on the temperature of the body corresponds to that of the temperature of its environment. So meaning a temperature could decrease, or the temperature of a body could decrease up to the temperature of its environment. So it is not possible, so for a certain body, so to decrease even below the temperature of its environment. And similarly, so there is a limit on the increase on the temperature of the body, and that limit is the temperature of its environment. The temperature of the body could not heat up, okay, could not warm up to a certain temperature, so greater than that of the temperature of its environment. So we have to take note of that. And solving this given differential equation, we could use separable equations, so similar with the growth and decay. So multiplying dt over the difference on the temperature, so that will yield to this one. So dt over t minus tm is equals to k dt. So since our variables here are the temperature and time, so tm here, or the temperature of the body, would be the variable. So tm here, or the temperature of the environment, is considered as constant. So thus, if we are going to let u, so to be equal to t minus tm, so that would give us du to be equal to dt. So getting our numerator, and thus the integral, okay, so of that given differential equation, so would be an ln, or the logarithmic function. So ln t minus tm is equals to kt plus c, and then exponentiating both sides, so that will give us our general equation. So for the Newton's law of cooling, so to be T minus Tm is equals to C EKT. So that is the general formula that we will be using for the Newton's law of cooling. So there are no other relations that we will be using or other equation that we will be using for Newton's law of cooling application. So other than this, because this is a law. So these are the different methods that we will be following in solving applications of Newton's law of cooling. The first one is this is the critical in solving problems involving Newton's law of cooling. So we have to properly identify. So we have to identify all the given. So in particular, so we have to differentiate. So which is considered to be the body or the object on the given problem. And then we have to consider as well, so which is the environment. Okay, so where is the object subjected into? So once we were able to identify those two, so we'll be able to resolve a given differential equation. So it would be easier so for us to substitute those things. And then afterwards, so we're just going to substitute the given so that we could use our general formula for the differential equation. And then afterwards, so we will just be resolving it. Let's have our first example. So it reads that a thermometer is taken from a room that is 20 degrees Celsius to the outdoors where the temperature is 5 degrees Celsius. So after a minute, the thermometer reads 12 degrees Celsius. So what will be the reading on the thermometer after another minute? So in solving problems involving Newton's law of cooling, so there are two things that we need to consider first. So we have to identify what is the object and what is the environment. So once we were able to identify those two things, so it would be easier for us to substitute those values to the given differential equation or to the formula. So in this given problem, so what is the object that we are, or what is the body that we are looking at? So there is a thermometer there. So a thermometer is an object. So therefore that would be our object, or that would be the body that we are looking at. So in this case, so I would underline it, and I would going to identify that one as the body that we are talking about in the problem. And then although in the environment, so we have to identify there are two environments that were mentioned here. So one is the room and the other one is the outdoor. But we have to consider is where is the destination of the object. So where are we going to place the object? So initially, the thermometer is on the room. However, so to change the temperature, so we are putting it outside, or we are placing the thermometer outside. So therefore, our environment there would be the outdoors. Okay, so not the room, because initially it's on the room. But the environment is where are we going to place the object, so for us, or for the body to change its temperature. So outdoors would be our environment. And from here, so we can draw our given. So initially, we have a thermometer, so which is inside the room. Okay, so if initially, so when time is equals to 0, so what would be the temperature of the body? So it does not directly mention what would be the temperature of the thermometer. However, initially it was placed on a room, so where its temperature is 20 degrees Celsius. So therefore, the thermometer reads temperature, and the room is 20 degrees Celsius. Therefore, initially, the reading on the thermometer is 20 degrees Celsius. And then afterwards, so we have the environment. So the environment is the temperature of outdoor, and it says there that the temperature is 5 degrees Celsius. So T sub M, so which is 5 degrees Celsius, so for our environment. And then it says here as well that after a minute of placing the thermometer outside, the thermometer reads 12 degrees Celsius. So since the room temperature is higher than the outdoor temperature, so we are expecting that once we place the thermometer outside, so there will be a decrease on the temperature. And true enough, after a minute, so there is a change already of 12 degree Celsius. And then we are asked to determine, so what would be the reading, or what would be the temperature of the thermometer, so after another minute. So that is another minute, so which is plus 1 minute from the original time that elapsed. So therefore, that would be similar to after 2 minutes. So that is what we will be finding. So what would be the temperature after 2 minutes? And this is what I have mentioned a while ago. So the change on the temperature of the body is limited up to the temperature of its environment. So initially, the temperature of the body is 20 degrees Celsius. And then after a minute, so it becomes 12 degrees Celsius. So there is a decrease, but it's still higher than the temperature outdoors, so which is 5 degrees Celsius. So therefore, after 2 minutes, so we are expecting that the temperature will decrease or will have a value lower than the 12 degrees Celsius, but of course, it's still higher than 5 degrees Celsius. So from there, we could already have an idea on what would be our answer. So we are already given a range for our answer. So that would be less than 12 degrees Celsius, but that should be greater than 5 degrees Celsius, because we cannot have a temperature lower than that of the temperature of the environment, since the change on the temperature is cooling or a decrease on the temperature, so up to 5 degrees Celsius only. So to resolve this one, so we're not going to derive the formula anymore. So we were able to derive it before. So we're just going to use it right away. And our formula then would be T minus T sub M. So is equals to CEKT. So that is our general formula. So the first thing that we will be substituting here, so would be our Tm, or the temperature of the environment, because that is constant. So that would be T minus, that is 5, is equals to CEKT. And again, so similar with the growth and decay, so we need two initial values. So for us to get the value of the arbitrary constant C, as well as our proportionality constant K. So from there, we'll be able to derive our general formula, so which pertains to the temperature of the body with respect to time. So following our initial condition that when time is 0, and that is initial time, so we are given that the temperature of the body is 20. So substitute that on our equation before, so that T is 20 minus 5 is equals to CEK, time is 0. And this is equivalent to 1. And thus giving us C to be equal to 20 minus 5, so which is 15. Then we have to substitute it again to our equation this time around. So we have C already, so that is T minus 5 is equals to 15 EKT. So the next thing that we will be getting, so after getting the arbitrary constant C, we will be getting the proportionality constant K. So to do that, so we will be using the second initial value, or second value. So that would be after a minute, so when T is equals to 1, the change on the temperature, so T becomes 12. So So substitute it. So that would be 12 minus 5 is equals to 15 E K, and then T is 1. So 12 minus 5 is 7 is equals to 15 E raised to K. And 7 over 15 would be equal to E raised to K. So taking the logarithm of both sides, so ln of 7 over 15 is equals to ln E raised to K. And that would give us K to be equivalent to ln of 7 over 15. So now that we have the proportionality constant K, so substitute it to our equation. So T minus 5 is equals to 15 E raised to, our K is ln 7 over 15. Then multiplied it with T. So I'll just going to write T first. So T ln of 7 over 15. So giving us our working equation that the temperature of the body, so minus 5 is equals to 15E multiplied with time, so ln times 7 over 15. So since we already have our working equation, so we can now find what is required, and that is what would be the temperature of the thermometer, so after 2 minutes. So when T is equals to 2, so what would be the temperature? So substitute it. So T minus 5 is equals to 15 E raised to 2 ln of 7 over 15. Or that would be simply as T 15E 2 ln of 7 over 15 plus 5. So giving us the temperature. So let me calculate it. So 15 E raised to 2 ln of 7 over 15, and then plus 5. So giving us the answer, so to be 8.27 degrees Celsius. Okay, so that would be 8.27 degrees Celsius. As you can see here, so after 2 minutes, so our answer is less than 12 degrees Celsius but higher than 5 degrees Celsius. So that would be 8.27 degrees Celsius. So that is for our first example. So simple as that. So let's have our second example. So it states that a metal ingot was heated to 50 degree Fahrenheit, then placed in an oven that was preheated to 150 degree Fahrenheit. So after 10 minutes, the temperature increased to 75 degree Fahrenheit. So how long would it take for the ingot to reach 100 degree Fahrenheit? We have to identify again, so what is our object and then what is our environment. So as you can see here, so we are talking about the metal ingot. So the metal ingot, so what is this one? This would be the scrap metal, so that was molten into a certain sheet, probably metal sheet, so that would be used for another material. Okay, so this would be the raw material, which are heated up. Okay, so for to be built or to manufacture another metal object. So that would be our object. So this is our object, and then the environment. So where are we going to place the metal ingot? So this is placed in an oven. So therefore the oven is our environment. So oven would be our environment. So since we were able to identify those things, so we could now write down our given. So I'll write first the temperature of the environment, since the first one that we are substituting. So the oven is preheated at 150 degree Fahrenheit. So 100 degree Fahrenheit, so that would be the temperature of the environment. And then initially, so the metal ingot was heated to 50 degree Fahrenheit. So when time is 0, so the temperature of the body is 50 degree Fahrenheit. And then after 10 minutes, so this would be our second, so after 10 minutes, so second value, so the temperature increases. Okay, so it increases to 75 degree Fahrenheit. So as you can see here, this one is about warming up a certain object, as opposed to the first example, so which is about cooling. We are tasked to determine, so how long will it take for the ingot to reach 100 degree Fahrenheit. So this time around, so we are to find the time. So when the temperature is 100 degree Fahrenheit, so what would be the time? So as you can see here, there is an increase on the temperature. So from 50 degree Fahrenheit to 75 after 10 minutes. So we are expecting that to reach 100 degree Fahrenheit, so the time should be greater than 10 minutes. And 100 degree Fahrenheit is still achievable. So since the temperature of the oven is 150, so which is the maximum possible temperature of the metal ingot. So for our solution, so we will be using the same formula. So T minus T sub M, so would be equal to CE KT. And then the temperature of the environment is 150, so that would be equal to CE KT. Substituting our initial value, that when time is 0, the temperature is 50. So 50 minus 150 is equals to CEK times 0. So this would be 1. So giving us the value of C, so to be equivalent to 50 minus 150, that is a negative 100. And substitute it again for C, so we'll have T minus 150 is equals to negative 100 EKT. And then the other given, that is when time is equals to 10, the temperature reaches 75 degree Fahrenheit, or just simply 75. And from here, so T is 75 minus 150. So 75 minus 150, and that would be equal to negative 100 E K, and then the time is after 10 minutes. So giving us negative 75 minus 150 is negative 75, is equals to negative 100 e raised to 10k. And negative 75 over negative 100 would be equal to e raised to 10k, or simply 75 over 100, so we have 3/4, so equals to e raised to 10k. And taking the logarithm of both sides, so that is ln of 3 over 4 is equals to ln of e raised to 10k. And then giving us the k then, so to be equal to ln of 3 over 4 all over 10. Okay, so for the value of k. So now that we have the k, so we can substitute it again. So that is T minus 150 is equals to negative 100, and then e raised to T ln of 3 over 4 all over 10. So that is our working equation. So now we are to find what is the time. So what is the time when the temperature is 100 degree Fahrenheit? So when T is 100, so what is the time? So how much time? So we're expecting it to be greater than 10. So let's solve it. So 100 minus 150 is equals to negative 100 e raised to T, then ln of 3 over 4 all over 10. And 100 minus 150 would be negative 50. So which is equals to negative 100 e raised to T ln of 3 over 4 all over 10. So negative 50 all over negative 100 then would be equal to e raised to T ln of 3 over 4 over 10. So this is 1/2. So 1/2 is equals to e raised to T ln of 3 over 4 all over 10. And then for us to get the value of T, so the exponential function should be removed. So we have to take the logarithm of both sides. So ln of 1/2 would be equal to ln e T ln of 3 over 4 all over 10. And that would give us to ln of 1/2 would be equal to ln e, so would leave us to T ln of 3 over 4 divided with 10. Simply 10 ln of 1/2 is equals to T ln of 3 over 4. Finally, the T would be equal to 10 ln of 1/2 all over ln of 3 over 4. So giving us the time to be, so let me solve it. So 10, so ln of 1/2, and then divide it with ln of 3 over 4. So giving us the answer to be equivalent to 24.09. So 24.09 minutes. Okay, so that is greater. That is what we are expecting. So greater than the 10 minutes. So 24.09. So that is another way of determining this time, the time, so instead of the temperature. So let's have another example. So for our third example, so it's a metal rod again. So a metal rod was heated to 1,000 degrees Celsius, then immersed in a cooling oil with a temperature of 20 degrees Celsius. After 15 seconds, the metal rod's temperature decreased to 600 degrees Celsius. So how long would it take for the temperature to decrease to 400 degrees Celsius? So this problem is similar with the first problem. So what is our object? A metal rod. So that would be our body. And where did we place the rod? Okay. So initially it is heated at 1,000 degrees Celsius, but afterwards it was immersed in a cooling oil. So therefore, the environment where we subjected our metal rod is a cooling oil, and that would be our environment. Okay. From here, so we can write down our given. So the temperature of the environment, which is the cooling oil, so that would be at 20 degrees Celsius. And then the temperature of the body, so initially, so it is heated at 1000 degrees Celsius. And then after 15 seconds, so where the metal rod was immersed into the cooling oil, so that is 15 seconds, the temperature decreased to, we have to take note here, the preposition that we are using. So in this case, we are using to. So when we are referring to 2, so that means that is already the final temperature. So 600 degrees Celsius. So 600 degrees Celsius. But if we found there that instead of 2, so it was written there that it decreases by 600 degrees Celsius. So we have to subtract it. Okay? The 600 from the original 1000. But since this is 2, so that pertains to, that's already the final temperature of the metal rod. So 15 seconds after it was immersed in a cooling oil. And for our required, so what would be the temperature of the metal rod? So after, what would be the time? So to make it 400 degrees Celsius. I know. So this is similar with the second, not the first. But this time around, so instead of increasing, so this is decreasing. So for our solution, so same, so T minus Tm is equals to CEKT. The temperature of the body or the environment is 20, so CEKT. And then when time is 0, so we have the temperature of the body to be 1000. So 1000 minus 20 is equals to CEK times 0. So where that is 1, so therefore C is equivalent to 980. So for our C, right, 980. So T minus 20 then would be equal to 980. Then E K times T. And then again, so after 15 seconds, so 15, so T drops down to 600. So 600 minus 20 is equals to 980. E, the time is 15. So this would be 580 divided with 980 is equals to e raised to 15k. So 580 divided with 980, that is the same as 29 over 49. And that is e raised to 15k. So taking the logarithm of both sides, so giving us k to be equivalent to ln of 29 over 49 divided with 15. And thus forming our equation to be T minus 20 is equals to 980 e raised to T ln of 29 over 49 divided with 15. So that is our final working equation. So we are to find what is the time. So when the temperature reaches 400. So what would be our time? So to do that, So we'll have the 400 minus 20 is equals to 980 ET ln of 29 over 49 divided with 15. So 400 minus 20, that is 380 over 980 is equals to E T ln of 29 over 49 divided with 15. So 380 divided with 980, that is 19 over 49, is equals to 80 ln of 29 over 49 divided with 15. So taking the logarithm of both sides, so ln of this and ln of that, so that will give us to t, so to be equivalent to 15 ln of 19 over 49 divided with ln of 29 over 49. So we are expecting that the time should be greater than 15. So let me calculate it. So that is 15 ln of 19 over 49, and then divided with ln of 29 over 49. So we have an answer, so which is equal to 27.09 seconds. So it would take 27.09 seconds, so for the metal rod, so to decrease its temperature into 400 degrees Celsius.